In the early morning darkness along the far northern California coast, the Earth delivered two reminders that the region sits atop one of the most complicated tectonic environments on the planet. At 3:53 in the morning Pacific Daylight Time, a magnitude 5.7 earthquake struck approximately 96 miles, or 154 kilometers, west-southwest of Pistol River, Oregon, at a depth of about 6 miles, or 10 kilometers. Less than 2 hours later, at 5:45 in the morning Pacific Daylight Time, a second earthquake measuring magnitude 5.1 occurred about 40 miles, or 64 kilometers, west of Petrolia, California. What immediately caught the attention of seismologists was not merely its magnitude, but its astonishing depth, only about 650 feet, or 0.2 of a kilometer, beneath the seafloor. Why did two moderate earthquakes occur within such a short period in the same offshore region? Were they connected through the same stress field, or were they separate releases of energy within a highly fractured crust? And what does the unusually shallow Petrolia earthquake reveal about the forces currently acting beneath one of North America's most active plate boundaries? These questions point to the hidden tectonic forces at work. Northern California's coast is dominated by the Mendocino Triple Junction, where three massive plates converge: the Pacific, North American, and Gorda plates. Offshore, the Gorda plate, a fractured remnant of the ancient Farallon plate, is being squeezed under North America along the Cascadia subduction zone, and it is bounded to the south by the east-west trending Mendocino fracture zone, a major transform fault. In this tangled boundary region, stresses from the neighboring North American plate and Pacific plate cause frequent earthquakes in the interior of the Gorda plate. In other words, the Gorda plate is unusually crumpled and broken. It is far from a rigid block. Numerous faults snake through the Gorda basin, creating a hotbed of seismicity even away from the main plate edges. As one geologist put it, this area could really rather be called a zone of deformation, with the Pacific plate pushing northward into the Gorda plate, generating many small faults and earthquakes within the plate. The two new shocks fit this pattern. Both occurred offshore of Humboldt County, just north of Cape Mendocino, a rugged region already known for frequent quakes. The Petrolia quake struck almost directly beneath the coastal hills of Humboldt at practically zero depth. That extreme shallowness, less than 0.62 miles or less than 1 kilometer, implies slip on a very near-surface fault, likely a branch of the Mendocino fracture zone, the southernmost extent of the fault separating the Pacific and Gorda plates. The Pistol River quake lay a bit farther north, still offshore on the California-Oregon border. While one epicenter was clearly in United States waters and the other barely offshore, both lie within the offshore part of the Mendocino Triple Junction, where three tectonic plates meet. In fact, scientists have long noted that Petrolia and its surroundings are rocked by repeated strong quakes, mostly from offshore faults related to the Triple Junction. This is no accident. The entire Mendocino region is the meeting ground of Pacific plate motion, subduction forces, and the torn-up Gorda plate. To uncover the nature of these quakes, seismologists turn to the moment tensor solutions, focal mechanisms derived from waveforms. In plain terms, this is like decoding the orientation of the slipped fault and the direction of motion during the quake. Both events' tensors indicate steep, nearly vertical fault planes with predominantly horizontal strike-slip motion. In both cases, one nodal plane trends roughly northwest-southeast, strike approximately 320 degrees, and dips about 85 degrees, almost vertical. The slip rake angle near negative 167 degrees is nearly opposite the fault strike, meaning the blocks slid past each other sideways rather than up or down. In short, these were sideways, strike-slip earthquakes. This fits the regional pattern. The Mendocino fault system and many Gorda plate faults are right lateral transforms. For example, the great 1994 magnitude 7.1 quake on September 1st, 1994, in this area was on the Mendocino fault and had a right lateral strike-slip mechanism. Likewise, the June 15, 2005 moment magnitude 7.2 shock, 91 miles or 146 kilometers west of Crescent City, ruptured on a northeast striking strike-slip fault within the Gorda plate. Indeed, The 2005 event serves as a template for understanding today's quakes. That moment magnitude 7.2 earthquake was caused by north-south compression of the Gorda Plate by the Pacific Plate. Scientists noted it occurred in the middle of the Gorda Plate to the west of the Cascadia subduction zone, and its mechanism was pure strike slip, with no significant vertical displacement. No tsunami was generated. Similarly, our two new shocks show little sign of the large vertical movement characteristic of subduction megathrusts. Instead, they imply lateral shear. The record shows the Gorda Plate is squeezed roughly north-south by the Pacific Plate's northwest motion. At bends or jogs in this transform, compression or extension can occur, producing some thrust or normal faulting locally. But on average, these offshore faults behave like a crinkled series of right lateral cracks sliding past each other. The moment magnitude estimates of the new quakes, moment magnitude 5.7 and moment magnitude 5.1, are modest by the standards of this region. But the energies involved are still huge. The Pistol River quake, released on the order of 4.2 times 10 to the 17th power Newton meters of seismic moment magnitude approximately 5.68, while the Petrolia event released about 5.2 times 10 to the 16th power Newton meters, moment magnitude approximately 5.08. These values, together with the nearly pure double couple solutions, reinforce that these were true fault slips, not exotic volumetric sources. In effect, each shook the crust with around 10 to the 16th power to 10 to the 17th power Newton meters of work, millions of times more energy than a kilogram dropping a meter, or 3.3 feet, or 2. What do these quakes tell us about the local geology? First, they underscore that the Mendocino region is highly active. Historical records show at least 3 really big earthquakes in this neighborhood. A moment magnitude 7.3 to 7.6 quake on January 31, 1922, west of Arcata, just south of today's shocks, which was felt from Oregon to Southern California. A moment magnitude 7.2 on June 15, 2005, west of Crescent City. And the moment magnitude 7.1 right lateral event on September 1, 1994, north of Cape Mendocino. These giant quakes were themselves likely strike slip on regional faults. The 1922 and 2005 shocks were deep in the Gorda Plate, and the 1994 shock broke the Mendocino Fault itself. By comparison, the devastating 1700 Cascadia megathrust quake was far larger, perhaps magnitude 9.0, but that was due to slip on the buried subduction interface. The fact that Northern California has seen several magnitude 7 and greater events means that today's moderate quakes are not unprecedented clusters. Instead, they are part of the churning tectonics in a place that regularly delivers surprises. Second, by analyzing the fault orientations of past quakes, geologists have mapped how the plates deform. For instance, the 2005 event's northeast strike and sideways slip fit models, where the Gorda Plate takes up Pacific North American convergence by internal strain. The plate is not rigid. The September 1994 quake, on the other hand, highlighted the Mendocino Fault as a critical transform. University of California researchers note that most of Petrolia's felt quakes come from offshore Mendocino Fault branches, hinting at creeping segments and locked patches along that boundary. Both today's quakes, then, are right at the interface where the Pacific Plate's westward push turns into subduction and lateral shear. The geological process at work is classic plate boundary dynamics. Imagine the Pacific Plate driving north-northwest. It grinds along the Mendocino transform against the Gorda Plate, which itself is being squeezed and forced beneath North America. In such a setting, stress builds up on any available fault. Eventually, some fault breaks. Blocks slide past each other, sending seismic waves outward. The recent Pistol River and Petrolia quakes broke along nearly vertical faults, imparting mostly horizontal shear motion. These are the kind of motions you would see on the Mendocino Fault or its splays, side-to-side sliding, rather than up and down. We can say these quakes were strike-slip events. In fact, United States Geological Survey moment tensors show one plane of slip for each quake with nearly horizontal movement on a steep fault. By contrast, a true subduction megathrust quake would show a high-angle thrust rupture, with one block riding up over another. Here, no vertical uplift occurred, so no tsunami was generated, a consistent sign of strike-slip activity. The inescapable conclusion is that these quakes were driven by the same compressive forces that caused so many others in the Gorda Plate. Finally, is there any special significance to the timing? We see two moderate quakes within hours, but they were separated by tens of miles, or tens of kilometers, and appeared on independent faults. Earthquake science suggests this is likely coincidence rather than a direct aftershock sequence. The Gorda region is simply always simmering. With stress being constantly loaded, the faults jiggle intermittently. Some worry, could these shakes increase stress on the Cascadia megathrust? According to Coulomb stress studies, quakes in the Mendocino zone do impart small stress changes to nearby faults, but such static transfer is usually limited to a distance roughly twice the fault length of the event. These magnitude 5 events rupture only a few miles, or a few kilometers, of fault, so their reach is small, unlikely to nudge the locked megathrust several tens of miles or several tens of kilometers away. In a nutshell, Northern California has just delivered a geological reminder of its restlessness. Two magnitude 5 quakes rattled the Gorda Plate's tangled web of faults, the kind of sideways slippage typical of this transform subduction junction. While these shocks were modest compared to the region's history of magnitude 7 and greater events, they are perfectly consistent with the rugged crust and stresses at the Mendocino Triple Junction. For seismologists, the importance is not sensational headlines, but science. Each tremor provides fresh data on fault orientations, slip distributions, and stress interactions. By mapping these microquakes, researchers refine their models of the plate boundary and ultimately improve understanding of what future tremors might bring.